Hello everyone, this is Dr. Hopkins with our next video in our series of videos for 472. Today we're going to use elementary reactions in a few short mechanisms. So the first one we're going to do is this reactions approaching equilibrium, and this is a one step where we have first order in the forward and first order in the reverse, so each one of these are represented as elementary reactions. And then we can write the rate of disappearance of A, because we know these are elementary reactions, as the forward rate constant times A minus the reverse rate constant times the concentration of B. If we were to set this up where we start with all A and let this start reacting, so that means that the B at times 0 is equal to 0. So A at times 0 is our total concentration at any point in time. So the sum of those is just our initial concentration. So then we substitute in for B. So we solve for B and substitute in so that we have just A. So it allows the integration to be a little easier. And we're left with these rate constants times the A of t minus the Kr times our A0. So let's integrate this. And then we look at that and we find that A of t, so integration out of this expression, gives us our concentration at any time is the initial concentration times a series of equilibrium constants forward and reverse and the exponential decay. And then we also can substitute in and solve for B, where it's just it's the equilibrium, or excuse me, the initial concentration and 1 minus this expression in terms of our rate constants. But maybe more importantly is we're looking at equilibrium. If we let this reaction run until its thermodynamic endpoint, right? So kinetics is the time dependent. Thermodynamics doesn't care about time. Eventually, the forward and reverse reactions are equal because we get no change in concentration of A and B at equilibrium. And so that we can set these two first order reactions equal. And then we know from thermodynamics that it's products over reactants. And if we're looking at the elementary reactions, it's just written this way, which would mean these are this ratio is the ratio of the rate constants, which is equal to our equilibrium constant. So that's how we can connect that time dependence eventually gets to our thermodynamic value, the equilibrium. Okay, so now let's look at something maybe a little more interesting in terms of, now let's look at some competitive reactions. So we've got two different products from one reactant. We're going to do first order reactions. So let's write the rate law. So the rate of disappearance of A is just K1 times A plus K2 times A. So we have two different routes, two different rate constants, both of them decreasing the concentration of A. And we substitute in, we rewrite it this way, and then we integrate it, and we know that A at any time t is our initial concentration times an exponential decay related to both routes of converting to products. Okay, so now what may be more interesting is to look at the appearance of products. And so let's do B first. So it's K1A. Now we have A at any time t, so we substitute that in. And then if we assume that we started with no products at all, and we only started with only reactants and let this go, then B at any time t is this ratio of constants, so K1 times this ratio of constants, and the exponential that we have. If we do C, we do the same thing, except now it's K2 times A, substitute in, integrate, and C at any time t is basically the same, except it's K2 times this constant. Okay, so let's look at these in terms of ratios. So if we were to figure out what's the concentration of B at any time t related to our reactant concentration, if we sum we're just going to substitute K for the sum of the rate constants, and this is just this exponential, and C would be this exponential. But what may be most interesting is the ratio of the products. So if we take these and we ratio them, the only difference is this K2 and K1. So our C over T is just the ratio of the rate constants because we are two first order reactions. All right, so let's look at a different mechanism. Let's look at consecutive first order reactions. So we're going to go from reactants to some intermediate to final product. So we evaluate our rate of disappearance of A. So we write our rate law based on this mechanism. It's just K1A, so there's one first order reaction, so we're not competitive. And then we get this for our A at any time t. So we could write also the rate of appearance or disappearance. It doesn't really matter. It would just be negative signs. But if we write the rate of appearance of the intermediate, it's just K1 times A. That's what's creating it. And then K2 times I is what's making it go away or turning into product. And we can substitute our answer for A in here. And we got K2I. And that means we can rearrange and solve for I. So I at any time t, or excuse me, we want to integrate for I, and we're left with this expression where it's a double exponential, one that creates it, one that makes it disappear. Okay, so our rate of appearance of product is due to this second step, so K2 times I, but we have an expression for I which we substitute N. And if we assume that we started with all A at the beginning of this process and just let it run, then we have this algebraic expression. So we know that P at any time t is just our initial reactant minus whatever the reactant is now minus whatever the intermediate is now. And so that means our rate of appearance of product is this exponential times our initial concentration. But it's probably more interesting to look at consecutive first order reactions if we look at the relationship between the two rate constants. So if K1 is much greater than K2, so that means that the second step in our process is a limiting reaction, or is the limiting step, then the rate of appearance of the product is K2 A0 e to the minus K2t. Right, so we remove any of the K1s, and then our product at any time t is equal to 1 plus this expression, which is equal, basically, it sums to 1 minus the exponential related to the second step. The rate limiting step is giving us our product, and our intermediate at any time t is just how fast it disappears. Right, so we're basically K1 is running so fast, is generating all intermediate, and then the disappearance or the concentration of intermediate is solely dictated by how fast it disappears into product. Conversely, if we set the first step as the rate limiting step, then our rate of appearance of product is dictated by K1, okay, and so we know K1A, so as soon as we produce, we want to think about it this way. We've got our product is related to our initial reactant because as soon as we produce I, it creates product because the second step is so much faster than the first step. So every time you produce the intermediate, it moves to product almost immediately. So that means that our concentration of I is small and isn't changing very much. And so then there's an expression of, at what point the maximum intermediate we can evaluate. And is this expression related to the ratio of the rate constants? Now, if we add reversibility to the first step and then add another product, another reactant, so we've got A plus B, we've got a pre-equilibrium, or we've got what we set up in the first part of this video, where we have reversibility in the first step and then K2 to the second step. So now our product, rate of appearance of product is still K2I. Our rate of appearance of I is now this expression. And if we allow the first step to go to equilibrium, so that means that the reversible process is so much faster than the production of product, then we can allow we can set up an equilibrium, a thermodynamic equilibrium for the first step, if you will. So when we have products over reactants, or the ratio of the rate constants, K1 over K minus 1. And so we know I at any time is our equilibrium constant times AB. And we can substitute that in for I in our differential with respect to the product, how much with our rate of appearance of product. And so we end up with this equilibrium times K2 and then A times B. So it's still related to our reactants initially. And so then it's just this sum of all of these rate constants. So the product of these rate constants over the reversible reverse reaction times our reactant concentrations. So basically we end up with a rate law predicted by a pre-equilibrium two-step mechanism that does not include the intermediate, and we shouldn't include an intermediate in any of our rate laws because our experimental rate law that we're going to compare it to is not going to have an intermediate. We run our experimental rate laws are with respect to reactants in terms of the reaction rates. So until next time.